All right, so for part 3, you'll actually need the text that you picked up on the way in. It's a very small chunk of text for the first one, but this is transitioning us into the key principles of ideal gases. So let's take some time right now to figure out what ideal gases are by reading the text and answering the questions. So our first question, actually you should pause, read the text, answer the questions, and then come back to the video to go through the answers to the questions. Why do we call them ideal gases? The reason we call them ideal gases is because we assume a lot of things about the gases, and because gas is so complex, there's so many molecules moving around, making these assumptions isn't the way that gases tend to behave all the time in real life, so we idealize them in our head to make it easier for us to analyze them. So we treat them as a system and not individual molecules. We talked about this before. It's because these particles are moving all over the place, and it would be impossible for us to track a single particle throughout gas. And the 4 key assumptions that we make are right here. The particles are so small that the volume of the particles is negligible. The attraction between the particles is 0, so there's no microscopic potential energy. The particles are in constant random motion, so there's macroscopic kinetic energy, and the collisions between the particles with surfaces are perfectly elastic, which means there is no loss of kinetic energy. Now let's talk about average speed. Though you'll not be required to calculate average speed of gas particles, again, because this is a complex formula, you should know the formula and what the formula means in terms of the key relationship between temperature and particle velocity. But before we look at this formula, let's make a guess. If you increase the temperature of a gas, so you make something hotter, what do you think is going to happen to the velocity of those particles? Will it increase or decrease? That's right, it will increase. I feel like Dora the frickin' Explorer over here. We know that increasing temperature will increase particle movement because they'll start to move faster and faster. Now, we already knew this relationship, but in the event that we're asked to determine how much the temperature increases by, let's make sure that we know the answer using the formula below. So we have our formula below, which is velocity of our gas, which is an average particle velocity, is equal to the square root of 3 RT divided by m. The key idea here to know is that when temperature is increased, velocity increases too. This is because velocity and temperature have a direct relationship. So right here it says C Mr. Lorette serial killer scratch work, and here it is. So I've taken this formula and I'm trying to isolate it to give us the, again, the relationship between velocity and temperature. So I want to get velocity and temperature on the same side of the equation. To do that, you can see the steps that I took, quite a few of them, which landed me over here with m isolated and temperature and velocity both on the same side of the equation. You can see here that the mathematic function between them is division, which means direct, but there's also something else special that we have this squared here. So it turns out that it is not only direct, but it is the square root of that direct nature. So what will doubling the temperature do to velocity? So say we increase temperature by a factor of 2, it will result in an increase in velocity, but by the square root of 2. If we increased temperature, let's do that, by 4, it results in an increase by the square root of 4. This is because of the inverse nature of having a square root under as in the denominator. So that's just something that we want to keep in mind. Now with average kinetic energy, we're switching to text number 2. Let's take a moment to read that text, and then we'll come back together to go over the answers. So our first question, what is the formula we use to calculate average kinetic energy? We can see that it's right here. There's this KB value in there, and our question is asking us what that KB stands for, and that's Boltzmann's constant. You do not need to memorize this for the physics, SAT physics exam. Again, you won't be using this formula, but it is important that we make determinations about the relationships. So what kind of relationship exists between the average kinetic energy of our gases and the Kelvin scale. So this is really important, and there's a side video that you can watch that explains why we talk about it in terms of Kelvin and not Celsius. But if you double the kinetic energy of the gas, we know that if we were to isolate it, it's going to result in a direct relationship between, well, let's do this real quick so we can see it. We have our average kinetic energy, let me write it over here, is equal to 3 divided by 2, Boltzmann's constant, time temperature. If we divide both sides by T, we can see, this is what we're interested in, this is the relationship between those two variables, that there's a direct relationship between kinetic energy and temperature. So if you were to double the temperature, it would equal a doubling of kinetic energy, the average kinetic energy, and vice versa. This is key that we do it with a Kelvin scale. And again, if you're interested, you can see why. I'm actually going to pull this page up right now. If you're curious why this works only for the Kelvin scale and not the Celsius scale, you can follow me down the rabbit hole by going to the video that I've created here. Though this video might make a little bit more sense after you've completed the pressure portion of this packet. Just a heads up.